Okay, so just kind of wrapping up, the different tests that we're talking about. We're going to do these last series right here, so we're analyzing whether it's convergent or divergent. First of all, when you look at a problem like this, you got to kind of know what test might apply best. The thing that I showed you on this one last time is you have a rational function. Now you can just kind of forget about the square root for a minute. And if you look at that, notice that's a rational expression. And this thing is off by a power of 2. Okay, so what we said that we would do on this, if you look back in your notes, we did what we called the limit comparison test. And what we're going to do with this one is, when you do a limit comparison test, I'm just going to review what it says. Anytime you're doing any of these tests, refer back to the theorem that's in your book, and it'll direct you through exactly what you do to apply that test. So what this is saying is you want to, a sub k is the sequence you have, so you're given a sub k right there. B sub k is what you're going to compare it to. Okay, so that's what we need to do. Need to have all positive terms in this. This is pretty easy to verify. A sub k has all positive terms because k is positive, right? That's going from 1 to infinity. Okay, now if you just ignore the square root, what is a series that you've learned about that is, pretend like the k is not there. I'll give you a hint here. 1 over something, k to something. Any idea there? P series, right. P series is 1 over k to the p power, right? Now these are 2 off, okay? So what we're going to use, I think we did something like this last time, is we're going to use the series k equals 1 to infinity of 1 over k squared, okay? So that's going to be, and we're going to use the square root though. I'm going to go ahead and put that back under the square root. And the reason I need to do that is to put it under the radical, okay? What I'm trying to do is when I do that ratio, I'm trying to make that ratio have a pretty simple limit. I want those powers to be the same. So it's off by 2, that's the reason I do that then. Okay, so that is a P series. And does that P series that I chose converge or diverge? Converges, how come? Because P is greater than 1, right? P is that exponent, okay? So the 2 is greater than 1. Okay, so if you now read what the limit comparison test does, what we've done is we've established that we have a series that converges. Okay, the one we're comparing it to converges. So what we need to do is we need to see if a sub k converges. So we could break it down to case 2, or in case 1, if we do the limit of our comparison, that's the ratio of these 2 series, and we get a finite number, then we're also going to get a convergent answer. Because if you get this case 1, if the series you already know converges, and we already know that the P series converges, then that will also converge. Okay, so that's what you do. So always go back and just, like I say, the theorem tells you what to do on these things. You just got to get yourself in mind what these theorems are doing. Okay, so here's what we're going to do then to begin to put this all together. So we've got B sub k is our convergent P series. So what we're going to do is we're going to do the limit as k goes to infinity, and we're going to do a sub k over B sub k. A sub k is what I gave you, so let's just write that down as it is. That's k over k cubed plus 1. And then you don't have to write it this way because you guys want to, save yourself a little bit of work. But what you're doing is you're dividing it by that, correct? Okay. So what you can do is you end up multiplying by the reciprocal anyway. So what we're going to end up doing on this is we're going to write this next step. Limit as k goes to infinity. We're going to have the square root of k over k cubed plus 1. And since we're dividing by this fraction, technically we're dividing by a fraction, then what we're going to do is we're going to multiply by the square root of k squared over 1 like that. All right, everybody with me okay? Okay, is that good? Okay, we're dividing kind of like the ratio test. We were dividing by a fraction, so we're multiplying by the reciprocal. Okay, next thing you're going to do is you're going to do this. we're going to do the limit, k goes to infinity, and they're both under a radical. That's the reason that I chose this right here to be like that. And okay, and I think I just overlooked something. I just caught it. Okay, and I'll explain that in just a minute. So let's go ahead and finish this. But I just caught something that I was not thinking through correctly. Okay, so if you multiply that straight across, you're going to have k cubed over k cubed plus 1. Okay, now let me pause there and correct what I did. Okay, I was getting a little bit ahead of myself. Okay, this thing really right here is not a p-series. Do you know why? Because I'm doing the square root. I forgot all about the square root. That square root's there. And the reason I have to choose this under a square root is so I can get it under that radical. I couldn't just use 1 over k squared. I got to use square root of 1 over k squared. Well, so what is that? Okay, what that really is that is the series k equals 1 to infinity of 1 over k. All right? Now I got to start over again, and we're still on the right track. But what kind of series is this? Harmonic. Good. Okay, what do you know about the harmonic series? It always diverges. Okay, so now our thought process, we're still forming our ratio. We're doing that fine. We're not making a mistake on that. I was just thinking p-series, I was forgetting about the radical. Everybody clear with what I'm talking about there? Okay, so what we want to do now is we want to go ahead and do this limit. We'll see which one of these cases apply when we do that limit then. Okay, so what we're going to have on this then, and you have a theorem that says if you have a limit of a radical, you can really write this like this. You can, by one of your limit theorems, you can say limit is k goes to infinity of k cubed over k cubed plus 1, all, and then the square root over the whole thing. Okay, that's a basic limit theorem that you can do. Okay, well, let's see. What is that limit right there? Do you guys know that just like that? What is it? 1, good. Okay, why is it 1? Degree of top and degree of bottom are the same. That's the easiest way to look at that. So if you learn to recognize that, then you can go ahead and just write that answer then. So really what you get is you get the square root of 1, so that's equal to 1 like that. Okay? So let's see what case applied then. So if you look at case 1, what we really got on this is we got 0, the value, you have this situation. So you have 0 is less than 1. That's what L is, less than infinity. So in other words, we got a finite answer to our limit. So the conclusion by the limit comparison test says that both series do the same thing. They either both converge or they both diverge. Okay, so if the harmonic diverges, what's the answer to our problem? Diverges also. Very good. Okay, so we would say, therefore, the series diverges by the limit comparison test. Okay?
So we can still use the basic k even though it's square root over 1 over k squared?
Yes. Now the reason I did it that way, the reason I put the 1 over k squared under a radical was because the series started under a radical. And the only way to get that under a radical is for it to be in a radical also. So in other words, like if I had the square root of k over k cubed plus 1, and if I just multiplied it by the p-series, that would never go under the radical, so it would never, and actually you'd be dividing by that, so it would never give us that limit that we're looking for. Generally what you want to recognize is if you have a rational function, whether it's under a radical or not, a limit comparison test is almost always what you do. And you try to get those degrees so that they become the same on the top and bottom. Okay, that'll help you a little bit on that. So when you see that kind of thing in your homework, since it's rational function, that will tell you limit comparison test is a good way to go.
So that was like k to the 4, we use k to the cube?
Yes, exactly. And see, you would have the square root of 1 over k cubed, and that would actually be a p-series. Okay, because then if you did the square root, if you had something like the square root, if you had something like the square root, come on, behave. If you had something like the square root of 1 over k to the third, like that, okay, that would be 1 over the square root of k to the third, so that would actually be 1 over k to the 3/2. That would be a convergent p-series because that exponent 3/2 is bigger than 1. Okay, so that's how that would work out. And that would be the approach, exactly. Okay, very good. Any other questions about what I did with that? Okay, all right. Next thing we want to look at is this one with the logarithm in it. Now, the thing on this one is comparison. I'm going to do this one with the comparison test, and I sometimes call that direct comparison test. So one thing that you could definitely do on this one is you can take the 5 out if you want to start the series that way. So I'm going to go ahead and do that. So that's just 5 times the series k equals 2 to infinity ln k over k. Now what we're going to try to do is we're going to try to do a direct comparison test instead of a limit comparison test. And that's because it's not a rational function. The numerator has an ln in it. And the other thing that I see is I see this. Something jumps out at me. Does it jump out at you? 1 over k. What is that? Harmonic series, right. So what we're going to go ahead and do is we're going to do this. We're going to go ahead and let b sub k, which is the series we're comparing it to, that's going to be the series, and we can go ahead and say k equals 2 to infinity 1 over k. The reason we can do that is one thing we learned is if you take off terms of a series, it does not change its divergence or convergence, okay? So in other words, the harmonic series goes 1 to infinity. That's the standard way. But if you make it go to infinity, you're chopping off one term, so it still diverges. Okay, if you take off terms, that doesn't change the convergence or divergence. Does that make sense? Now, if it converges, it'll change the value of the convergence, but it won't change the fact that it converges. Does that make any sense? Okay, so we're deleting a term on that, so that's how that goes. Okay, so what we're going to do, if you look at the comparison test basically says this. We have established that we have a series b sub k that we know diverges, because what we're doing is we're working with again, a harmonic series, and we know that that diverges. So let's just follow exactly what it tells us to do. Okay, well, you can forget about case 1 because we're not even comparing it to a convergent series. So we need to basically see if case 2 holds. Okay, so what are we looking for? We're trying to show that b sub k is less than or equal to a sub k. If it is, then since b sub k diverges, so does a sub k. So again, I'm doing exactly what that test tells me to do. That's what you got to do. All right, so let's do that. All right, so what I'm going to do, I'm not going to worry about the 5 or anything, so I'm just going to do this. So I'm going to just say a sub k. I'm going to go ahead and put the 5 back in. It actually doesn't matter. I just want to do that, I think. So I'm going to say, just go back to the beginning, and we're going to do this. We're going to try to show that 0 is less than b sub k is less than or equal to a sub k. Okay, so we have 0 is less than b sub k. b sub k is the series with 1 over k. Now you're just doing the expression. Is that true? 1 over k is always greater than 0. Tell me that. Yeah, of course. K is a positive number, right? That's the counter on your series. Now we need to see, is that less than or equal to where we started, 5 ln k over k. All right, we need to see if that's true. Well, what you have is you have really like a proportion here. And the way I look at this is like this. If you have 1 over k less than or equal to 5 ln k, over k, what we're going to do is I'm going to try to see if this is true. So you can actually do this. You could actually multiply both sides by k, and you've got to be real careful about that on an inequality. Here's why. First of all, is k a positive number in this problem? Of course, it's going from, k is going from 2 to infinity. If you multiply both sides of an inequality by a positive number, nothing changes. The sign doesn't change, right? What did you learn if you multiply an inequality by a negative? Sign changes. So we don't have to worry about that. But we can do that. Okay, so what we have now is we have 1 is less than or equal to 5 ln k like that. Okay? Well, ln kind of has different values on this. Now, one thing on an ln is sometimes it's bigger than 1, sometimes it's between 0 and 1. So what I'm going to go ahead and do on this one is I'm just going to solve this kind of like it's an equation. So if I divide by 5, I would have 1/5 less than or equal to ln of k. And you would find that that's sometimes true. It's not always true. So what I'm going to also do on this is just kind of look at graphically something on this. So if you remember your ln graph, let's see kind of what we know. Tell me what the ln of 1 is. 0. Okay, so we have that. All right. And then if you have the ln of something greater than 1, your graph goes like that, right? And then if you're between 0 and 1, you end up having these fractional values, okay? Now remember, in our problem, k starts at 2, right? Everybody agree? Okay, so if you look at this, if k is greater than or equal to 2, would that be true? Absolutely, because if you do the ln of 2, you're going to be in this positive part of the graph, okay, like that, all right? And then what you'd have to kind of do on this, if you went through and finished that a little bit, you could even go through and write this in exponential form. So you could say e to the 1/5 is equal to k, like that. So as long as k is bigger than that, then you're going to be okay. So since k starts greater than or equal to 2, that means that you're going to be fine with that. Okay, so that means that that's going to be true. Therefore, in our comparison test, since we're comparing it to a divergent harmonic series, now we can conclude that this also diverges. Okay, and that's by just the comparison test, not the limit comparison test. Okay, now see, a lot of what I'm doing there is kind of stuff in my head in a way. I'm just trying to verify that this inequality is always true. Okay, and it is based on what I know about graphing, that kind of thing like that. Okay, all right. So I want to show you one other thing on this problem before I leave this. You could also kind of do something on your calculator if you're unsure on this. So like if you did the ln of 2, remember k starts at 2. Okay, you would have 0.69, right? Okay, what are you comparing it to? You're comparing that to 1/5. Okay, that does it right there. Okay, you can do that if you want to. Okay, all right, does that make sense to everybody what I was trying to do with that? Okay, so one of the things can't stress enough is when you're doing a test, just go to your theorem. Your theorem tells you what to do. Okay, that's what you learn in higher math, is always go back to that definition, always go back to that theorem, and it'll guide you the right way, okay, if you understand it, that is. Okay, let's do this last one then. And again, one of the things you're trying to learn how to do is how to know what test applies to which situation. We talked about this one in the last class, and what I generally said, if you have something to a k power, we said that root test was good, right? Okay, or even if you had like a 2k power or a k squared power, a root test is a really good thing to try. So that's what I'm going to do on that. I went ahead and just put the theorem up here because as I'm teaching this, you want to refer to what that's saying, okay? So what we're going to do is we're going to do the root test. And the root test basically says you want to make sure that your infinite series has all non-negative terms. That's actually a fairly easy thing to do in this problem, because what you're going to end up having, if you look at this part right here, okay, well, what's going to happen to 1 over k? If k is 1, you're going to have 0, right? Okay, this is kind of important on here. So if k is 1, you would have 1 minus 1 over 1 to the 1 squared power. Wouldn't that be 0? But that is non-negative, right? Okay, it says the root test only works for non-negative terms. So if you do have a negative term, you can't use it. Okay, and that's because you would have a square root of a negative number. That's the reasoning for that. But beyond that, everything's going to be positive. So if you went to the next one, if you went to k equals 2, you'd have 1 minus a half over 2 squared. That'd be 4. From there on out, you're positive. And the reason I know that is because that exponent's always going to be positive. You square k, it's going to be positive. So we're good. Okay, but you got to check little things like that. That's important. Don't overlook that condition of the theorem. Okay. Now what we want to do is we use rho as what our textbook uses. So you want to write down that we're doing the limit of k goes to infinity, and then we're going to do the k root of, let's see, the sequence that we're working on is 1 minus 1 over k to the k squared power, like that. Okay, so that's what we're working with then. So what we need to do is work on that particular limit for a little bit. This one has a little bit of work to it, so I might not have given you a lot of room on your notes. Just do the best you can. Okay, so first of all, if you do this, can you tell me what after you do the k root of k squared, what you would have? Because remember, you just divide exponents, right? So what you would have, you don't necessarily have to write this down, but you would have, really you would write this as 1 minus 1 over k to the k squared over k, right? And then that would just be k. That thing right there is going to go to k. So you want to make sure you know the algebra. So let's write this down. This is limit k goes to infinity of 1 minus, doing the wrong thing there. Let's do parentheses 1 minus 1 over k to the k power, like that. Okay. And then let's kind of take it from there then. Okay. Now this thing right here looks like something, you even do this in Calc 1 when you do Lhopitals Rule. Okay. This thing right here, if you put this in, let me show you what happens. If you put infinity in right now, what would happen? You would have 1 minus 1 over infinity to the infinity power. Okay, that thing goes to 0, correct? So what do you really have? You have one of these indeterminate forms, right? Okay, so that means Lhopitals Rule is what you need to do on this problem. Okay, look for that and don't forget about Lhopitals Rule. So what you learned how to do in this case, in Lhopitals Rule, anytime you have an indeterminate form with exponents, like infinity to the infinity, 1 to the infinity, any of those indeterminate forms, you want to do this like this. Let's just choose a variable and let's let t be equal to the limit as k goes to infinity of 1 minus 1 over k to the k, like that. Now what's a slick trick to get this k out of the exponent? Do a logarithm. You can do a logarithm of both sides. So we're going to do ln of t, and you can go in the limit and do the ln like that. Okay? So let's kind of take it from there and see where this leads us then. So we'll have ln of t is equal to the limit as k goes to infinity. Then move that thing down, so that would be k times 1 minus 1 over k, like that. Okay, let me close OneNote because I hate it when that stupid error comes out. So let me reopen it real fast. Sometimes something will get stuck. I don't know why, but that arrow when I'm writing drives me crazy. Okay, all right, well, let's push on from here then. Okay, all right, so what we have now is if you went through and kind of saw what we have now, you need to do one more step on this when you do this. Before you can really do Lhopitals Rule, you need to make sure it's a 0 over 0 or infinity over infinity. So what I'm going to do is I'm going to do kind of a slick little trick here. Then you can kind of see if this makes any sense to you. You've done this before. You do this even in Calc 1. I'm going to write that as 1 minus 1 over k all over 1 over k. So first of all, tell me if you understand why that's right, algebraically. Yeah, because what are you doing? If you divide by 1 over k, you're multiplying by k, right? And that's what I was doing anyway. Now, why did I do that? Okay, what would be the value of the limit of the numerator if k goes to infinity? It'd be what? Okay, and then on the denominator, what would you have? Oh, hold on, I forgot about my ln. Okay, sorry. So that needs to have an ln there, like that. So that would be the ln of 1, right? What is the ln of 1? 0. What would be the value of the denominator if you go to infinity? So we have a 0 over 0 limit. Is that clear to everybody? Okay, you're just doing the limit of 1, right? Because if 1 over k goes to infinity, it goes to 0. Agreed? Okay, are we good? Now the reason I did 0 over 0, rearranged it that way, is so I can use Lhopitals Rule. So on Lhopitals Rule, tell me what I need to do. I need to do the derivative of the top and the derivative of the bottom. Okay, that's what I need to do. So I'm going to kind of go over the side with some, scratch paper here a little bit and just work these things out. So I'm going to go on and write this as ln of t equals, I always put this LH just to remind myself that now I'm doing Lhopitals Rule. Okay, so I'm going to have the limit as, again, k goes to infinity, and then let's just do these two derivatives. Now I'm going to write this as ln of 1 minus k to the negative 1, okay, just so I can do that derivative. Okay, when you do the derivative of that, you're going to get 1 over the function, which is 1 over 1 minus k to the negative 1, times the derivative of what's inside, which is, by power rule, would be 2k to the negative 2. Okay, so I'm going to go ahead and just write that as it is. That's going to be 2k to the negative 2. You can leave it as a negative exponent or make it positive. I'm just going to start this way to kind of see what I have there. So that's the derivative of the top. Okay, now if I do the derivative of the bottom, let's see, the bottom is 1 over k. So if I do the derivative of k to the negative 1, that would be negative k to the negative 2. Okay, so I can go ahead and then I can write this like this as negative k to the negative 2, like that. Okay, so I think I'm okay. Now I just saw a mistake. Maybe you guys saw it too. Where in the world did this 2 come from? I don't think that was supposed to be there. What was I doing when I did this derivative here? So I'm being a little sloppy. Okay, it's 1 over this. The derivative of the inside part is just what? 1k to the negative 2. Oops. Okay, so I've corrected that. Everybody see that okay? Now that's a basic derivative. It's just a logarithm derivative. Okay, so that 2 should not be there. Now I love the way this thing's working out. Okay, all right, everybody with me? Okay, now these things right here would really cancel out. So because what you really have on this is the derivative of the top here, and then this is the derivative of the bottom. Okay, and what you're really doing, you don't have to write this down, but you're doing k to the negative 2 over 1 minus k to the negative 1, and you're dividing by this thing, right? If you're dividing by this denominator, then you're really multiplying by its reciprocal. Okay, so those things are going to cancel out. Okay, you don't have to write that. You can do it in your head if you want to. You can put that over 1 and then just see how those things cancel out. So that's kind of nice. You do have that leftover negative though. Okay, so now what we're going to have is ln of t is equal to the limit as k goes to infinity of, and we're left with, I've got that negative there, so I'm just going to put that in the numerator, and I've got 1 minus k to the negative 1, so I'm going to write that as 1 minus 1 over k like that. Okay, so that's what I should end up having right there. So are you okay with what I've done so far? This is kind of a Lhopitals Rule review, and you got to be really careful about everything. Now, what I can do from here is I can go ahead and do my limit now and see what I get. So if k goes to infinity, then where does this whole limit go to? Negative 1, right? Okay, it'd just be negative 1 over 1, right? Because the denominator would go to 1. Okay, so what you'd end up having is you would end up having this. You would have ln of t equals, and then when you do that limit, that's going to be negative 1 over 1. Okay, agreed? Okay, so now we have ln of t equals negative 1, and then you want to write this in exponential form. That's a base e, so you would say e to the negative 1 equals t. So in other words, t, which is the value of our limit, is 1 over e. So there's a tendency when you kind of go off to a side like this to forget even what you're doing, but we're doing the root test, okay? What we just found is we found the value of rho. We found the value of this limit. So 1 over e falls in case 1, doesn't it? 1 over e is less than 1 and it's bigger than 0. So what you would have is 0 is less than or equal to 1 over e is less than 1. That's case 1. Okay, so now you're ready to conclude that this diverges, or converges, sorry. So we would say, therefore, the series converges by the root test. Okay, so sometimes you get into limits that take a little bit more work. Okay, I didn't give you a lot of room on the paper, I don't think, so sorry about that. Okay, does that look okay? All right, is there any question about anything I did? Okay. All right, that's kind of a typical thing you have to do sometimes is go off to Lhopitals Rule, so don't forget about that. Okay, that'll wrap us